All right, let's talk about something that feels a little bit like magic. We're going to be demystifying convolutional neural networks, or CNNs. This is the technology that literally teaches computers how to see and is powering everything from your phone tagging your friends in photos to self-driving cars navigating busy streets.
But how does that even work? How does a machine look at a bunch of pixels? At the end of the day, it's just numbers, and somehow know, hey, that's a cat, or that's a stop sign. Well, the answer lies in the brilliant architecture of convolutional neural networks.
So here's our game plan. First, we'll cover what a CNN actually is. Then, we're going to pop the hood and look at all the building blocks. After that, we'll follow an image on its journey from pixels all the way to a final prediction. We'll check out some amazing real-world uses, and finally, I'll show you how you can get your hands dirty and start building with CNNs yourself.
Okay, let's dive right in. Before we get into all the nitty-gritty details of how it works, we've got to get on the same page about what it is. So what exactly is a convolutional neural network?
You can think of a CNN as a special kind of artificial brain. It's a deep learning algorithm that's been built from the ground up to understand visual information. It's inspired by our own visual cortex, and it's fantastic at finding patterns in images, which makes it perfect for all sorts of computer vision tasks.
So, how does it pull this off? How does it actually work its magic? Well, let's break it down and look at the core components, layer by layer. This is where things get really cool. The absolute heart of any CNN is the convolutional layer. The best way to picture this is to imagine a bunch of tiny magnifying glasses, or filters, scanning across the image. Each filter is a specialist. One is an expert at finding vertical lines, another looks for the color green, and a third might be looking for a certain rough texture. As they scan, they create these things called feature maps, which are basically treasure maps showing where in the image they found the feature they were looking for. And the process itself, the convolution, is actually pretty simple. As that filter slides over the image, it's just doing some simple math. It's basically asking, at every single spot, how much does this little patch of the image look like the feature I'm searching for? The answers to that question, a whole grid of them, make up that new feature map. Now, for all you engineers watching, this is where you get to take the wheel. You can control how these filters work. You can change the kernel size, how big your magnifying glass is. You can set the stride, how many pixels it jumps at a time. And you can add padding around the image to make sure you don't lose information at the edges. These are the key knobs you can turn to tune your network.
So right after the convolution, the data gets passed through something called an activation function, and the one you'll see almost everywhere is ReLU. Its job sounds almost too simple. It just takes any negative number and turns it into a zero. That's it. But this one tiny step is absolutely crucial. It introduces something called nonlinearity, which is what lets the network learn really complex patterns instead of just simple straight lines.
And this isn't just a theoretical thing, it has a massive practical benefit. It's been shown over and over that networks using ReLU just train faster. And when you're dealing with millions of images and huge models, faster training is a total game changer. Okay, so after our convolutional layer has created all these detailed feature maps, the pooling layer steps in to kind of simplify things. Its job is to shrink the feature maps down, which does two really important things. It makes the network faster and more efficient, and it helps prevent it from getting bogged down in tiny irrelevant details. You'll generally run into two types of pooling. Max pooling is the most popular by far. It just looks at a little window of the feature map and keeps the biggest number. It keeps the strongest signal. This is great for making sure the most important features get passed on. Then there's average pooling, which, you guessed it, just takes the average of all the values in the window.
All right, we've got all the building blocks now. We've got our convolutional layers, our ReLUs, our pooling layers. So let's put it all together. Let's follow an image on its complete journey, from being just a bunch of pixels to becoming a final confident prediction.
So, everything kicks off with our input image. Now, to the computer, this isn't a picture of a cat. It's just a big block of numbers called a tensor. It has a height, a width, and a depth, which for a color image is usually 3 layers deep, one for red, one for green, and one for blue.
In the very first layers of the network, the filters are learning to spot really basic stuff. Think of it like a baby first learning to see. It's not looking for faces or objects yet. It's just recognizing simple things. A sharp edge here, a diagonal line there, a change in color.
Now this is where the real magic happens. As the information flows deeper into the network, the layers start combining those simple features into more complex ideas. It might see a couple of curved lines and a circle and say, hey, that looks like an eye.
It might combine some pointy shapes and say, that's starting to look like an ear. It's building up a complex understanding from simple parts, just like Legos. Okay, once the network has found all these interesting features, the eyes, the ears, the whiskers, it's time to make a decision. First, a flattened layer takes all those 2D feature maps and just unrolls them into one single long list of numbers. This list, which is basically all the evidence the network has gathered, gets fed into a fully connected layer that weighs everything and makes a call.
And for the grand finale, we hit the softmax layer. This layer takes the final scores from the network and turns them into clean probabilities that all add up to 100%. So instead of some weird internal score, you get a clear answer. In this case, based on all the evidence, the network is 98% sure that it is looking at a picture of a cat. How cool is that? So we've gone deep on the how, but let's zoom back out and talk about the where. Where is this technology actually making an impact? Let's look at some of the incredible ways CNNs are being used out there in the wild right now.
And the truth is, they're everywhere. They're in hospitals helping doctors spot tumors in medical scans. They're the eyes of self-driving cars, identifying pedestrians, bikes, and other cars. They can even process audio, which is how your phone knows when you say, "Hey Siri." They're used to generate brand new synthetic images, and of course, they classify billions of photos on social media every single day.
Okay, so you're probably thinking, this is amazing, but it sounds really hard to build one from scratch. And you know what? It can be. But the good news is you absolutely do not have to start from square one.
The secret weapon for anyone wanting to get started with CNNs is a technique called transfer learning. This is your shortcut. It's the fastest, most effective way to start building really powerful computer vision applications.
Here's the big idea. Why reinvent the wheel? Giants like Google have already spent tons of time and money training massive models on millions of images. These models are already experts at seeing edges, textures, and shapes. With transfer learning, you can take one of those powerful pre-trained models and just fine-tune it on your own, much smaller dataset. It's way faster, way cheaper, and you can get incredible results with just a few hundred images instead of millions.
So there you have it. We've seen how CNNs can take a simple image, break it down into its fundamental features, and build up an understanding of what's inside. We have effectively given machines a sense of sight. And that leaves us with a really big and really exciting question. Now that they can see, what should we teach them to look for next?